Voyager 1 is a small bus-sized spacecraft launched in 1977 that has now traveled beyond the influence of the Sun's solar wind and entered interstellar space. Moving at the speed of 17 kilometers per second, which is about 61,000 kilometers per hour or roughly 38,000 miles per hour, it has seen Jupiter's storms, Saturn's rings, and then just kept going and going and going. Today, it is farther from us than any other human-made artifact in history. But that leads to the question, what is actually keeping Voyager 1 moving at such a high speed through space? Voyager 1 continues moving through space not because of any ongoing propulsion, but because of fundamental physical principles governing motion in a near-vacuum environment. After its launch and planetary flybys provided the necessary speed, no significant force exists in deep space to slow it down. Unlike on Earth, where motion is constantly resisted by air drag and friction with surfaces, interstellar space is almost entirely free of such opposing forces. The density of gas and dust is so low that the spacecraft can travel billions of kilometers with essentially no measurable deceleration. The key principle at work is inertia. Once Voyager 1 was set in motion at high speed, it remains in motion unless acted upon by a substantial external force. In practical terms, no such braking force is present. There is no atmosphere to push against the spacecraft, and there are no large bodies constantly colliding with it or absorbing its energy. Space is not perfectly empty, but the few particles it encounters are too sparse to matter dynamically. Voyager's thrusters are not used to keep it moving forward. They fire only occasionally for attitude control, that is, to rotate the spacecraft so that its antenna points toward Earth or to keep instruments aligned. These brief firings adjust its orientation, not its forward velocity, and do not meaningfully change its trajectory. The spacecraft is therefore not driven through space in the way planes or cars are driven on Earth. It is coasting. Gravity still influences Voyager 1, but not in a way that stops its motion. The Sun and planets continue to exert gravitational pull, gradually bending its path and slightly reducing its speed over long periods. However, the speed it acquired from launch and gravity assist maneuvers is high enough that gravity cannot pull it back into the solar system. Instead of falling inward, it moves outward on an escape trajectory, while gravity quietly reshapes the exact curve of its path. So the next question that may come to your mind is, if space has rocks and asteroids, why hasn't Voyager 1 hit anything? Popular movies make it look that way, but reality is different. Space is overwhelmingly empty. Even the asteroid belt, often imagined as full of tumbling boulders, is so sparse that a spacecraft can pass through it without ever coming near anything. Voyager 1 is tiny compared to the cosmic distances involved. The probability that it collides with another large object is so small that it is effectively negligible. The real threats are subtler and slower: dust grains hitting the spacecraft at high speed, radiation aging its electronics, and the freezing cold of deep space. But giant impacts are extremely unlikely. It will keep traveling for millions to billions of years. It will outlive our languages, our nations, our buildings, and perhaps even our species. It will drift among the stars, a durable metal fossil from a brief technological civilization that once lived near a yellow star. Now some of you may be wondering, will we be able to communicate with Voyager 1 forever? The answer is no. Voyager 1's greatest limitation is electrical power. Too far from the Sun for solar panels, it relies on radioisotope generators. These devices turn heat from slowly decaying plutonium into electricity. As the material decays, the heat output weakens, and therefore the electrical power falls year by year. That means engineers must turn off instruments one at a time. Heaters go next. Eventually, there will not be enough power even to run the transmitter. Most estimates suggest that contact will likely cease sometime in the 2030s.